swiper just stole my notes for the physics final.
Oh man, what was on it?
Light wave properties and behaviors.
What's that?
Well, from what I remember, here. Alright, sit down. And I'll teach you. So light waves are transverse waves, which means they move perpendicular, to the propagation of the wave. So parts of these waves include its wavelength, which can be measured from crest to crest, trout to trout, or similar points. And let's see, wavelengths determine color, with red having the longest wavelength and violet having the shortest. Amplitude, see, from here to here or here to here, determines brightness, and then there's frequency. Now you can find frequency using the formula V equals lambda times, you can find velocity, I'm sorry. You can find velocity by doing V equals lambda times frequency. And remember, it's measured in hertz, which is denoted by Hz. Oh, and I almost forgot. Actually, since it's light, it's no longer V. It's denoted by a lowercase c. Now, don't ask me what that means. I don't know why it's a lowercase c, but it just is. And c is actually a constant at 3 times 10 to the 8th meters per second.
Aren't sound waves and light waves the same thing?
Actually, no. See, the main difference is that light waves are transverse waves. Now, sound waves, see here, they're longitudinal waves, which means they travel parallel to the propagation of the wave. Let's see, what else? Also, sound waves must travel through a medium, whether it's solid, liquid, or gas. But light waves can travel through a vacuum, and I don't mean this vacuum. I mean a place where, a space where there is no matter and conditions are well below normal atmospheric pressure. And also, they can both reflect, refract, diffract, and interfere.
I know what reflection and refraction are, but what is diffraction and interference?
Well, I'll tell you. Diffraction is kind of like refraction, but instead of bending to pass between two mediums, like a solid and then to a liquid, the waves have to bend to pass between two objects, such as two slits. So like, imagine if there was a door, the waves would have to diffract to go through the door, while the waves have to refract to go through a solid into a liquid. This causes the perceived irregular blobs you see when you look at light. So now interference is a little bit different. Now there's constructive interference, which creates a bright fringe as seen here. See all these bright spots? And then there's destructive interference. Here, I'll change that to a D, which creates these dark fringes right here. Now, if we were to look at them like this, you can see that constructive interference, there's the amplitude superposed to create a larger amplitude. And then destructive interference can be seen when two amplitudes superpose to cancel each other out. The waves must emit the same wavelength at the same time period to interfere. Of course you know this from learning about sound waves.
That was so helpful. Thank you.
Hey, no problem. Where are you heading off to?
I'm going to the library.
Oh, okay. Well, you better watch out for that swiper. But good luck.
I will.
Hey Dora, what are you doing here?
Hey, I'm here to try and cram for my physics final.
Me too. I'm having a little bit of trouble on mirrors and lenses.
Hey, I actually know about that. Do you need help?
Would you? That would be so helpful.
Okay, so in this diagram here, the ray of light approaching the mirror is known as the incident ray, which can be labeled as I, or in this case, it is A. The ray of light that leaves the mirror is called the reflected ray, which can be labeled R or B. At the point of incident, where the ray strikes the mirror, a line can be drawn perpendicular to the surface of the mirror. The line is known as the normal line, which can be labeled N. The angle between the incident ray and the normal ray is known as the angle of incidence. The angle between the reflected ray and the normal is known as the angle of reflection. These two angles are labeled with the Greek letter theta, accompanied by a subscript. read as theta I for angle of incident and theta R for angle of reflection. The law of reflection states that when a ray of light reflects off a surface, the angle incident is equal to the angle of reflection. So do you have that down so far?
Yeah, keep going.
Okay, now let's talk about identifying characteristics of an image formed by a plane and a convex lens.
Okay.
A plane mirror is a flat mirror that reflects light in a regular way. A plane mirror reflects rays of light so they can change their path. All mirrors can create virtual images. The image appears behind the mirror and is reversed that the light rays are reflected back to your eye at equal but opposite angles. A convex lens, parallel light rays passing through are bent inward toward the focal point. The image of a convex lens is upside down and always smaller than the actual image. Since that's covered, let's move on to using ray diagrams to predict the image orientation, location, magnification, and types of convex lens.
Let's do this.
The distance from the lens to the focal point is called the focal length. Typically, a point is also noted that is 2 focal lengths from the lens and labeled 2f. If an object is outside the 2f, the image will be between f and 2f, smaller than the object, inverted, which is upside down, and real. If the object is at 2f, the image will be greater than 2f, bigger than the object, inverted, and real. If it is at f, there will be no image, and if the image is less than f, the image will be behind the lens, magnified, erect, and virtual.
Interesting.
Yes, there is also a way to do ray diagrams with algebra instead of drawing lines on graph paper. It's called the thin lens formula.
Ah.
The thin lens formula is a mathematical way to do ray diagrams with algebra instead of drawing lines on graph paper. And the equation is 1 over d naught plus 1 over d initial, which equals 1 over d final. D naught is the object distance in centimeters. D initial is the image distance in centimeters, and d final is the focal length in centimeters. Did you know that light travels in coiled optic fibers?
Really? That's so cool. Wait, what is coiled optic fibers?
Well, most optical fibers made today consist of at least 2 parts: a core through which the light is transmitted, and a protective cladding, either glass or plastic, that surrounds the core and helps prevent light from leaking from the core. The cladding bends or reflects inward the light rays that strikes its inside surface. A detector, such as a photosensitive device or the human eye, receives the light at the other end of the fiber.
Ah.
Okay, amiga, that's all I've got for you.
Thank you so much. The final starts in a couple minutes. Don't be late.
Well, I guess we should start heading up to class. I think I have everything I need.
Hey Dora, you ready?
Yeah, I think so. Is there anything else I need to know?
What have you learned?
Well, I already knew about mirroring lenses, but I just learned magnetism, modern physics, thermal energy, and light wave properties and behaviors.
You don't know about the electromagnetic spectrum?
Wait, I need to know that?
Yes. Here, let me help you real quick. I'm going to teach you about the electromagnetic spectrum and the different regions causing it. Okay, starting with the shortest wavelength and inversely a higher frequency comes the gamma rays. Used often in chemotherapy to kill cancer cells, these high-energy rays are produced in nuclear explosions and supernovas. Moving forward with increasing wavelength and decreasing frequency, X-rays come next. X-rays are used by doctors and dentists to provide a visual of bones and even airport security to see objects inside bags. Following that, ultraviolet rays comes from the sun, causing the body to produce vitamin D and tanning the skin, which leads next to the only part of the spectrum that we can see. This light is visible to the human eye coming from light bulbs, flashlights, or anything that glows, in addition to allowing us to see color. Moving past visible light, infrared light is observable using night vision goggles and can also be faintly seen with heat waves. Microwaves follows as it is used to heat food and observe outer structures of other galaxies. Lastly comes radio waves that are the longest wavelengths and the lowest frequencies of the spectrum. This form is used with music on the radio, satellites, radars, and computer networks.
Wow, that's really helpful, Boots. Thanks.
That's not all. When dealing with wavelength and frequency, an inverse relationship is shown. C, or the constant of the speed of light, constantly remains at 3.0 times 10 to the 8th power. The formula used would be C equals lambda F, showing the relation as an increase in wavelength would lead to a decrease in frequency and vice versa. Light, however, does not come in one form, as it has a dual nature to it.
Really? What do you mean by that?
Okay, as you can see, light can actually behave as both a particle or a wave. Light travels in a straight line as a particle, but also has the ability to bend around objects, proving its wave characteristic. Last but not least, the photoelectric effect that light has to offer. When the light and energy approaches metal, the energy is transferred to the electrons, giving them the ability to eject from the surface. This enables the use of solar power as solar panels convert the light to currents. And that's it. Good to go.
Wow, that's it?
Ding!
Wow, right on time. Thanks, Boots.
No problem. Good luck to you.
Good luck.
Thank you.
Yes.
Yes! Oh man, we did it!
You're gonna come in the wheelchair later when we do the side
Okay.
scene. Okay, go.